Hi everybody, this is the first of 3 videos that I'm recording for you about computer networking. The ways that computers talk to each other so that information can be shared from one to another, so that you can use files from another computer, run programs from another computer, talk to users on another computer, and so on. So, we're going to get started with video 4A, connecting computers. The first thing that has to happen for computers to talk to each other is that physically a signal has to get in between one computer and another. Computers read zeros and ones. That can happen with a wired connection or with a wireless connection. For a wired connection, there's several different types of wiring. The most typical these days that you're going to see is unshielded twisted pair. You'd recognize this as an Ethernet cable, a Cat5, a Cat6 Ethernet cable. Maybe you have some wired connections at your school or your home where you plug in the wire with the little clip on the back in the back of your computer, and then you click it into a network connection somewhere. There are other types. You may be familiar with coaxial cable that is often used with cable television. Fiber optic connections are possible, and in fact they're fairly prevalent, but not generally coming right to the computer. That's usually used for the long distance hauls, and the last bit coming to your computer is generally not, oops, sorry, the page changed there, is generally not fiber optic. Or wireless connections are getting more and more prevalent. You're familiar with Wi-Fi connections. There are Bluetooth connections. There are infrared connections. Some people have keyboards or mice that connect via infrared. Mostly those are being replaced by Bluetooth for short distance connections, and Wi-Fi is just getting bigger and bigger. Okay, connecting signals. Well, if we send a bunch of zeros and ones, we want the zeros to be zeros and the ones to be ones. Yet if we're sending an electrical signal, whether that's going as radio waves through the air or a signal on a wire, interference is quite possible. Because of noise in the transmission medium, it's possible for one of these bits to change between sender and receiver. So a very common way of guarding against this is to use parity checking. And we'll go over this right now. Here's a typical way to do parity checking. To each set of 7 data bits, an 8th bit is added. Or maybe to every 8 bits, a 9th bit is added. Or to every 9 bits, a 10th bit is added. But typically, for every set of 7 data bits, an 8th bit is added. And this is called the parity bit. Now, if you add 7 data bits and you add the parity bit, you now have an 8-bit code word, 7 bits of which you care about. 7 bits of which are the data you're trying to send. Maybe it's part of the music that you're streaming. The sender sets the parity bit for each code word so that the total number of ones in the code word is even, either 0, 2, 4, 6, or 8. So suppose you had a code word that, or your data was 11111111, 7 ones in a row. Wow, that's an odd number of ones, so you'd make the parity bit 1. So you'd have an even number of ones. Maybe your original data was 10000100. There were 2 ones in there. It's already even, so the parity bit you'd add would be 0. The receiver then looks at each code word, looks at every group of 8 bits. If the total number of ones is even, it says, oh, must have worked. Either all the data is correct, or we didn't have just 1 bit go bad. It's possible for 2 bits to have gone bad in exactly the right way, and that you wouldn't notice that error, but no 1 bit out of those 8 could be corrupted without you knowing. So if the total number of ones is even, it strips off the parity bit and then uses the original 7 bits of data. If the total number of ones is odd, it discards this code word and then requests from the sender a retransmission of that byte. So this is called even parity. And it could just as well be implemented as odd parity, as long as both the sender and the receiver agree. Now, there are other error detection methods besides just simple parity checking. And these other methods have some advantages and disadvantages. Generally, the advantages are there are more types of errors they can detect, and the disadvantages are it takes a little bit more time to do this. Remember, if you have to do this on every single byte of data that comes by, you want something that's going to work pretty fast. So in assignment 4A, you and an assigned partner will research one of the following 3 error correction methods. This is other than parity checking. One of them is called checksums, one is called cyclic redundancy checks, or CRC, and one is called forward error correction. Now, you and your partner can pick any one of those 3, and there's more data when you look at the assignment on the GOA website. You'll pick any one of them. You'll look at both text and video references for it. There's some nice YouTube videos put out there by third parties that show examples of how these work. And you're going to come up with a 1 to 2 page description of how the error detection method that you picked, checksum, CRC, or forward error correction, how it works, including an example. You've got to actually include something that shows here's the bits, here's what's done to them, here's how you check to see if there was a problem. Or alternately, instead of a 1 or 2 page description, you could create a 5 to 10 minute video that shows this. You'd still have to describe how it works and work through an example. Your choice. Be creative. Be whatever is going to work for you and your partner. Okay. Now that we can send ones and zeros from one computer to another, we've got to know how we're connecting these computers to each other. And right now, we'll just look at local area networks. In the beginning of computer networking, back in the 1980s, when the first local area networks came around, there was a big controversy on how you were going to connect all of these PCs that are in an office to one another. One of the first ways that it was done was via a bus. A bus was just a cable, a wire that went throughout your office, and each computer hooked up to that bus. Now, suppose this computer down here in the bottom left corner wanted to send something to this computer. It would put the information on the bus. It would travel along here. This computer would have to find something that was addressed to it and read it, send something back. Now, there's some problems with this. Suppose this wire right here had a break in it. You know, there was a problem with the wire. Then this computer could still talk to these 2, but couldn't talk to these other 3. And another problem was a lot of collisions of data along this main bus. Everybody's putting their data on the main wire. Maybe that's good, maybe it's not. Another one that became popular in the 80s but now is almost never used anymore was a ring. Each computer is connected to the next computer, to the next one, to the next one. So each computer is only connected to 2 computers. If this computer on the top wants to talk to this computer on the bottom, it can send data either direction, and it goes through a couple more computers before it gets there. Some advantages of this: any one break in the wire, there's still a path. There's a break right here. This top computer can get all the way through here. A disadvantage: every computer keeps reading all of the data that's addressed to somebody else and passing it on. It gets to be a little inefficient when there's an awful lot of data. So this topology isn't used very much anymore. A star topology is everything is connected to something in the center. Now, it doesn't physically have to be in the center. This is the way the bus has evolved. Basically, the bus is now included inside this device. You may have, for example, a wireless router at your home or a wired router, and all of the computers connect to this one router. They send a signal just to the router. The router sends things back and forth to the appropriate computers. It also is probably the one that has a connection to the internet. And so the star topology is the one that seems to have won out and is used almost everywhere now. Still some bus networks, still some ring networks, and there are some other hybrid topologies. Now, there's some more information on network topologies. I'd like you to take a look at this video. I'm not going to put this video on in the middle of my video. You're going to have to go to it yourself. This is a lesson from a free tutorial on how to earn a CompTIA Plus or a CompTIA A Plus certification. This is a certification that a lot of network technicians are required to get in order to get a job or maintain their job. There might be folks at your own school who do tech support that have this sort of certification. To get the certification, you got to study an awful lot of things on PCs, Macs, networks, and so on, and then pass some standardized tests. This is a lesson from a free tutorial for people that are studying up on it, on network topologies. So why don't you take a look at that? Now would be a good time. Thanks.